This presentation is on multicollinearity or simply collinearity, and I'm Pat Obi, Purdue University, Calumet. And here's what we mean by multicollinearity. When two independent variables, x1 and x2 in a multi-regression framework such as this, are collinear, it means that the two of them are correlated with each other. So generally, in any multiple regression specification, if two or more of the independent variables are correlated with each other, then we have this problem of multicollinearity. And how is this a problem? Remember, in a multiple regression study, we assume that the independent variables are independent of each other. That's why they are called independent variables. Only y may depend on x1 and x2, not the other way around. All right, the x's shouldn't depend on each other, and definitely they shouldn't be depending on y. And therefore, when we run a regression, we are assuming, when we make a specification such as this, we're assuming that each of these independent variables contains a unique piece of information about y, so that in addition to learning about how y's behavior is dependent on the joint behavior of x and y, we may also be interested in learning about how each of these independent variables impacts y. So continuing with that thought, if we have a specification such as this, we believe that the coefficient of x1, b1, which is the slope of b1, we believe that to be equal to the change in y for a unit change in x1, with x2 held constant. So when we wish to observe the unique impact that x1 has on y, we want to be sure that x2 is not a disturbance in that assessment. Likewise, b2 is the measure of the change in y, the dependent variable, for a unit change in x2 with x1 held constant. So again, b2 is expected to convey to us the unique impact that x2 has on y without x1 being in the midst of that inquiry. However, when multicollinearity exists, in that the two independent variables x1 and x2 are correlated, then as you can see, b1 is no longer going to be the change in y for a unit change in x1 with x2 held constant. Neither would b2 be measuring the change in y for a unit change in x2 with x1 held constant. So it is important that we understand full well what the implication of a multi-regression specification really is. The implication being that yes, in a multiple regression, we're seeking to observe how y relates to x1 and x2 combined. But within that assessment, one may also be interested in learning about the unique impact that x1 has on y without x2 being a meddler. And likewise, we may also be interested in learning about how x2 impacts y without x1 being a disturbing factor. So for those of you with a calculus background, b1 is considered a partial derivative. It's partial y partial x1 with x2 held constant, and b2 would be partial y partial x2 with x1 held constant. So that's what these coefficients measure in a mathematical way. When we have multicollinearity, all kinds of bad things can happen. First of all, the variances and therefore the standard errors of the regression coefficients, which are b1, b2, b3, are going to be inflated. In other words, they are going to be larger than they're supposed to be. Keep in mind that in calculating the t-statistic for each of the coefficients when you run a regression, that t-statistic is equal to the value of that coefficient divided by the standard error of the coefficient, as you can see here. So what this means is if we have collinearity, then in all likelihood this standard error here is going to be much larger than it's supposed to be, so that when divided into B1 will result in a low t statistic, which may cause us to which may cause us to accept the null hypothesis that x1 has no impact on y. The second one is that the magnitude of the coefficient itself may actually be different from what we expect. The magnitude, the size of this coefficient may turn out to be much smaller than we expect it to be, something like that. Thirdly, and this is important, sometimes when we have collinearity, the signs of the coefficients may be the opposite of what we expect. For example, you may be expecting that if you're looking at the relationship between a firm's earnings per share and advertising expenses. For example, your earnings per share is a measure of profitability. You would be expecting that earnings should go up if the firm increases its advertising budget, because it'll create increased awareness of the firm's product. And so the coefficient of advertisement should be positive, but then when you look at the sign of that coefficient, it turns out to be negative. And then there's a few others here that you may also be interested in learning about, the most important of which is the last one here, that in some cases the F statistic, which is a measure of the significance of the entire regression model, may be significant, but the t values, which measure the significance of the individual variables with respect to their coefficients, may not be significant. So there's a couple of ways that we can test for collinearity. One is a casual empirical examination, which is simply looking at the correlation coefficients between the x variables, and if the value of this correlation coefficient is too high, we might judge those two variables to be possibly collinear. A more rigorous inquiry, though, would be to calculate what's called a variance inflation factor. Now, this is interesting because to calculate the variance inflation factor, we're actually going to be running a regression of each independent variable against the rest of them. As you see here, we're going to regress x1 and x2 and x3, regress x2 on x1 and x3, and regress x3 on x1 and x2. If we have a multiple regression specification of this nature with 3 independent variables. And then how do we get this guy right here called VIF? Well, when we run this regression, for example, of x1 against x2 and x3, we're going to find the coefficient of determination in that regression and plug it into this formula, and then what we calculate is called VIF. What does it tell us? If it's too high, it tells us that we have multicollinearity. And the rule of thumb used by a lot of researchers is a VIF of more than 5. If VIF exceeds 5, then you might conclude that perhaps you do have collinearity problem in your model. Now, what does the number 5, or for that matter, as I explained here, a VIF of 10 mean? It means that the variance of the coefficient, which, remember, if you take the square root of it, it becomes the standard error of the coefficient. Well, this means that the variance of the coefficient is 10 times what it should be had there not been any collinearity. So, if there is no collinearity, VIF should be about 1. So let's look at a quick example, and we'll get back to these solutions in short order. So going forward, it says here it's believed that increases in the tar and nicotine contents of a cigarette are accompanied by an increase in the carbon monoxide emitted from the cigarette smoke. You wish to model carbon monoxide content Y as a function of tar, nicotine, and weight. And so you have this 4-variable model with 3 independent variables. Alright, so now here's the data set and here's the results. Don't forget, when you're running this regression, this is the data set that you just saw on PowerPoint. Alright, to run your regression, you'd go to data, then you go to your data analysis, you look for regression right there. Okay. And then your y, start from y and go work your way down, and then click here for the x values. Highlight all three of them, making sure that they are placed side by side. Check labels here. Output, click right there while cursor is blinking there. Let's go down somewhere nice, like about here. Alright, and then we okay, and that's our output. So that's the output right here, and we can see that this regression has a high coefficient of determination. We can see, most importantly, that f is statistically significant. Looking at the p-value, which is virtually 0, it's less than 1% and definitely 5%. So now, but there's a couple of funny things going on here. Now, it is true that we should begin our assessment of the validity of a regression model by first looking at the f statistic, which we can see here, f is significant. Now, we can also see that r squared is pretty healthy, which tells us that the explanatory power of the model is pretty high. So r squared is a measure of goodness of fit. So this is a pretty good fit. But though, look here at the t-values of the independent variables. Look at their corresponding p-values, and we see here that most of the t-values are not significant, even though we have such a huge r square right there. And as you can see, only the t-value for b1 is statistically significant. b1 is the coefficient. This is b1. It is the coefficient for x1. x1 is tar. Thirdly, observe that we would expect b2 to be positive, the coefficient b2 here to be positive and not negative. b2 is the coefficient for x2. x2 is nicotine. Shouldn't we expect that as the nicotine content of tobacco increases, that carbon monoxide emission should rise? So as you can see, this goes contrary to our intuition. It's counterintuitive. And so these inconsistencies suggest that multicollinearity may be present. So what are we going to do? We're going to first of all do causal empiricism by looking at the correlation metrics, the correlation coefficients of these independent variables. To do so, go to Data, go to Data Analysis, and go up here and click on Correlation and OK. Now get only the values of the x variables. Do not include y. There you go. Get all of these. Check labels there, outputs, and click here. While cursor is blinking there, let's go down somewhere here and dump it so it registers right there. That's okay. Alright, and that's it right here. Alright, I did that already. So you can see here in particular that the correlation coefficient between x1 and x2 is pretty high. Remember, the highest value of correlation coefficient is 1. So this is telling us that these two independent variables are almost perfectly positively correlated. A very high suggestion that these two variables may be collinear. There might be moderate collinearity between x1 and x3 and between x2 and x3, but for sure we know that something fishy is going on between x1 and x2. To do a more rigorous analysis, we need to calculate the variance inflation factor as you see here. To do so, what I did here already is to arrange my data sets. I'm going to regress x1 as you see here against x2 and x3. That's the data set arranged in that order. Regress x2 against x1 and x3, and I've arranged my data set to reflect that, and ditto for x3 against x1 and x2. So for example, when I carry out this regression, I'm just going to go to Data, Data Analysis, go down to Regression. Okay. Now I'm going to go ahead and delete everything I did before. Alright, now click back here, Input Y range, and then I'm going to go here. Now my Y would be my X1. There you go. and then click here for the x variables, and for the x variables I highlight these two. They have to be right next to each other. Alright, and that's it right there. And then I've already checked labels for output. I click right there while cursor is blinking. I look for where to dump it, and perhaps around here would be good. So okay, I already have my output over here, and you can see x1. You can see the regression I just ran right here. This is variance inflation factor. Looking at the formula, all I did was to go equal 1, which is the numerator, divided by open parenthesis 1 minus r squared, and this is r squared right here. The computer gives it to you. Alright, and that's how I got this 21.63. In the same way, run regression of going down here, x3 against x1 and x2, and also run x2 against x1 and x3, and get their variance inflation factors. Here they are actually. So I'm going to go back to PowerPoint so I can show you the summary of everything I've done. Alright, first off, this is the basic regression output, which we've already interpreted, and this is the observation we've already made, which, as you can see, most of the t values are not significant even though r squared is very high, noting that only the t value for B1 is actually statistically significant. Those for B2 and B3 are not. And then we did the correlation metrics and observed that this high correlation coefficient here appears to indicate that x1 and x2 are collinear. And then we then proceeded to calculate the variance inflation factor, running first this regression of x1 and against x2 and x3, and we found a pretty high VIF, meaning that the variance of x1 is more than 21 times as large as it should be. So that's pretty high. So for sure there is collinearity between x1 and one of these other independence variables. To know which one it is, we also run regression of x3 against the other variables and find a low VIF. So as you can see, the collinearity is not going to be between, I go back, it's not going to be between x1 and x3 because x3 has a low VIF. So we do the same for x2 against x1 and x3. I didn't show the result because I need not. You already know how that's going to be obtained. But when I calculate the VIF, I find it to be almost 22, meaning that the variance of x2, the variance of B2 rather, is about 22 times as large as it should be. Keep in mind, the variances we speak to here are with respect to the coefficients, not the variables. So back over here, if I said it incorrectly, this means that the variance of the coefficient of x1, which would be B1, is more than 21 times as large as it should be. And then going forward, it means that the variance of the coefficient of x2, which would be B2, is almost 22 times as large as it should be. So surely, as you can see, just like as the correlation metric suggested, x1 and x2 are indeed collinear. So what do we do? So if I go back here, that says solutions for collinearity. The first one here says drop the variables causing you the problem. You could do that, especially if you have a lot of independent variables, say about 4 or 5 or 6. You could say, okay, I'm going to remove the 6th or the 5th variable because you may still have a bunch of others to deal with that can help you explain why. But don't be quick to do this though, especially if you're working with only 2 or 3 independent variables. You don't have to dispose of any variable, because as number 2 tells you, if all the x variables are retained because you really want them in the model to help explain the behavior of y, then you should avoid making inferences on the individual beta parameters. In other words, you don't have to say anything about what B1 represents or what B2 represents in terms of B1. If I go forward here, in terms of, for example, B1 is a measure of how changes in tar would affect y, holding x2 and x3 constant. You can't say that, and you don't have to say that, by the way. Neither should you go ahead and say that B2 will tell us the impact that nicotine, X2, would have on carbon monoxide emission with X1 and X3 held constant, because as you can see, X1 and X2 play hanky-panky with each other, so you really can't isolate the impact that either X1 has on Y or X2 has on Y. Therefore, if you choose to keep the entire model, which may well be your goal, then you should avoid making inferences on the individual parameters with respect to the individual variables. If your goal in a multiple regression is to simply observe the relationship between y and all the x's combined, then stay with it. But if your goal is to also speak to the individual impacts that each of the x's has on y, then with multicollinearity present, you should be very careful. And this concludes this presentation on multicollinearity.